Ramanujan, of course, was a genius like very few. But there's an interesting story about him, which is narrated in a book by Robert Carnegie. Let me begin by reading an excerpt from that book. Ramanujan himself was far more realistic about his achievements. K.S. Srinivasan, a student at Madras Christian College, who'd known Ramanujan back in Kumbakonam, dropped by to see him at summer house. "Ramanju," he said, "they call you a genius." "Hardly a genius," replied Ramanujan. "Look at my elbow. That will tell you the story." It was rough, dirty, and black. Working from his large slate, he found the quick flip between writing hand and erasing elbow a lot faster when he was caught up in the throes of his work than reaching for a rag. "My elbow is making a genius of me," he said. Carnegie describes Ramanujan's style of working. And work it was, in expressing mathematical entities, performing operations on them, trying special cases, applying existing theorems to new realms, but some of the work too was numerical computation. Every rational integer was his personal friend, someone once said of Ramanujan. As with friends, he liked numbers, enjoyed being in their company. Even in the published notebooks, you can see Ramanujan giving concrete numerical form to what others might have left abstract, plugging in numbers, getting a feel for how functions behaved. Some pages look less like mathematical treatise and more like the homework assignment of a fourth grader. Numerical elbow grease it was, and he put in plenty of it. One Ramanujan scholar, B.M. Wilson, later told how Ramanujan's research into number theory was often preceded by a table of numerical results, carried usually to a length from which most of us would shrink. Ramanujan was doing what great artists always do, diving into his material. He was building an intimacy with numbers. For the same reason that the painter lingers over the mixing of his paints, or the musician endlessly practices his scales. Professor Hardy, with whom Ramanujan worked, has this to say about how Ramanujan worked. He worked far more than the majority of modern mathematicians by induction from numerical examples. All his congruence properties of partitions, for example, were discovered in this way. But with his memory, his patience, and his power of calculation, he combined a power of generalization, a feeling for form, and a capacity for rapid modification of his hypothesis, which was often really startling, and made him, in his peculiar field, without a rival in his day. So it is clear from all the people who knew Ramanujan that Ramanujan was an experimenter. He was experimenting with numbers. He was doing numerical calculations. He was searching for patterns. We may call him an experimather. Like there is experiment, there is experimath, where you do experiments to discover patterns in mathematics. What we are going to do today is to do some Experimath, and we are going to use the book from which Ramanujan taught himself to be a great mathematician. What we are going to do today is some experiments in mathematics. But these are not experiments on pencil and paper. These are experiments in constructing things. And we are going to use some formula from the book which was Ramanujan's teacher. There's no doubt in anybody's mind that Ramanujan's greatest teacher was a person whom he never met. That was a person called G.S. Carr, who wrote a book of some several thousand mathematical results arranged in a definite sequence called the Synopsis of Mathematics. And Ramanujan worked himself through many of the examples in this book, and in the process became a great mathematician. G.S. Carr, in his preface to his book Compendium, writes like this, and I will read out from the preface of his book. The work of which the part now issued is the first installment, has been compiled from notes made at various periods of the last 14 years and chiefly during the engagements of teaching. The work is intended in the first place to follow and supplement the use of the ordinary textbooks, and it is arranged with the view of assisting the student in the task of revision of bookwork. To this end, I have in many cases merely indicated the salient points of a demonstration or merely referred to the theorems by which the proposition is proved. I am convinced that it is more beneficial to the student to recall demonstrations with such aids than to read and reread them. Let them read once, but recall often. The difference in the effect upon the mind between reading a mathematical demonstration and originating one wholly or partly is very great. The difference between reading a mathematical demonstration or originating one wholly or partly is very great. It may be compared to the difference between the pleasure experienced and the interest aroused when in the one case a traveller is passively conducted through the roads of a novel and unexplored country, and in the other he discovers the roads for himself with the assistance of a map. G.S. Carr's book Synopsis of Elementary Mathematics was that map with which Ramanujan himself discovered the roads which later took him to unknown and unexplored territories, some of which are still being explored today. Let us now explore a little bit of that territory. There are some formula which G.S. Carr has mentioned in his synopsis, and I will read those formula out to you. They are there at page 92 and item 276. Sum of the powers of the terms of an arithmetical progression. So he has this formula, he has this formula for the sum of the first n squares, he has this formula for the sum of the first n cubes, and he has this formula for the sum of the first n fourths. So the book itself has pages like this. There are many formula, and Ramanujan apparently worked each of these formula out in his own way by experimenting, by experimathing. And now we are going to experimath, but not in the way that Ramanujan experimathed. We are going to experimath with things. We can add on pencil and paper, we can join with things. So we are going to now explore some of the formula in G.S. Carr's book, the book called Symposium, the book called Synopsis, from which Ramanujan taught himself mathematics. And to do those experiments, we are going to use things. With pencil and paper we add, here we join. So this is a number 4, this is the number 3, this is 4 plus 3, and when we add two numbers to themselves, this is 3 plus 3, this is an even number. This is an odd number. So the first experiment that we do is to study the properties of adding even numbers and odd numbers. I have an even number here. This is also an even number. And I add an even number to an even number, and we see that this number also has to be even. Now, as we saw, an odd number is an even number plus 1. So this is an odd number. This is an odd number. This is an even number. So an even number plus an odd number is, that's right, odd. And this is an odd number, this is an odd number. So an odd number plus an odd number is even. We can prove this, of course, with algebra, but this is a proof with shapes, joining shapes. Addition is joining. And now let's take this principle for some more examples. I take an odd number and I can break it up to make an L. With both sides of the L, both arms are equal. These two equal arms give me the even number, and this one in the corner is the plus 1. So this is an odd number with L's with equal arms. So this is one odd number. This is another odd number. This is a third odd number. And of course, this is the first odd number, 1, 3, 5, and 7. Now addition is joining. So let us now add the odd numbers in sequence. 1 plus 3 plus 5 plus 7. I add 1 plus 3 and I get this shape. I add that to the next odd number and I get this shape, and I add this to the next odd number and I get this shape. Whether this or this or this, all these shapes are squares. So we have proved that if we add the odd numbers in sequence, what you get is squares, which you can verify with pencil and paper. Alright, this is easy, you say. So let's go to a slightly more difficult example, which is there in G.S. Carr's book, and that is the sequence, adding in sequence the natural numbers 1 plus 2 plus 3 plus 4 plus 5. Let us go to a slightly more complicated example, and that is the sum of the natural numbers, the counting numbers 1 plus 2 plus 3 plus 4, which, as you know, works out to n into n plus 1 divided by 2. We can make the natural numbers 1 plus 2 plus 3, and as you see, the shape that you get is a triangle. We can also make the numbers with these cubes, joining the cubes. So this is 1 plus 2 plus 3 plus 4. And we get a ladder. We can also look at this like a triangle. When you do it on the plane, it looks like this. When we join the cubes, it looks like this. And now we notice that I can join two of these triangular numbers like this, and what I get is a rectangle. So this was the sum of the numbers up to the fourth one, 1 plus 2 plus 3 plus 4. This was also the same number. We can call it S4. So S4 plus S4, that is 2S4, is equal to this. So one side is 4, the other side is 4 plus that 1. So if this is n, this is n plus 1. The number of cubes is n multiplied by n plus 1. But there are two S4s in n into n plus 1, so S4 is n into n plus 1 divided by 2. This is the formula that we get from this little Experimath. Alright, So we know that the odd numbers added in sequence give me squares. We know that the numbers added in sequence give me a rectangle divided by 2, half the rectangle. So now you may ask, what is the sum of the squares of the natural numbers added in sequence? That is also a formula in entry 276 of G.S. Carr's book. And let us do that. So now we are going to Experimath with the sums of squares of the integers. Addition is joining. This is 1 squared, this is 2 squared, this is 1 squared plus 2 squared. And I have kept 6 pieces of 1 squared plus 2 squared. 1, 2, 3, 4, 5, 6. And notice how I've kept them. And now I'm going to add these 6 pieces. Addition is joining. Addition is joining 1 squared plus 2 squared. Now I'm adding 6 of these pieces together. Let me do it. Three pieces. And these 3 pieces also, I add them, putting them together. And now I add these 3 pieces to these 3 pieces. And lo and behold, what do I get? I get a cuboid. And we all know the formula for the volume of a cuboid. That is the length by breadth by height. So the breadth is 2 because we added 1 squared plus 2 squared. This is 3 and this is 5. So S n squared for n equal to 2 is 2 multiplied by 3 multiplied by 5. 2 into 3 into 5. Now let's look at S 3 squared, 1 squared plus 2 squared plus 3 squared. So now let's do the addition up to n equal to 3. This is 1 squared plus 2 squared plus 3 squared. Addition is joining. I join them to make this kind of a pyramid. And now I have taken 6 such pieces, that is 6 n squared for n equal to 3. And notice how I have placed them. I have placed them such that this is a mirror image of this, this is a mirror image of this, and this is the mirror image of this. And it looks very easy when I'm going to do it. When you do it, it may not be so easy, but that's the fun of Experimath. Experimathing until it works. Eureka! So now let us add these 6 pieces to each other. That is 6 sigma n squared for n equal to 3. So I add the first two pieces and add the third piece. I get this. I do the same thing here. I add, so this is 3Sn for n equal to n squared for n equal to 3. This is also the same. And now I've got these two pieces which I put together, and eureka! Again I have a cuboid. Volume 3 times 4 times 7. I hope you're convinced that if I go on to do this for n equal to 4 also, I will be able to make this cuboid. So let us look at the formulas. N equal to 2, 2 into 3 into 5. N equal to 3, 3 into 4 into 7. So this is n. What is this? N plus 1. And what is this? This is 2n plus 1. So 6 times sigma n squared is n into n plus 1 into 2n plus 1. And therefore one of those pieces is 1/6 of n into n plus 1 into 2n plus 1. And we get the second formula in item number 276 of G.S. Carr's Synopsis of Elementary Mathematics. So now, of course, you will ask the question, can we do the addition of the cubes? 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed and so on. Well, here we are. We have these pieces made here right before us. But of course, those of you who know integration know that addition is a discrete version of an integral. So the integral of 1 is just x or n. 1 plus 1 plus 1 plus 1 is n. The integral of x is half x squared. That is why we get the half here in that formula, half n into n plus 1 for sigma n. Integral of x squared is 1/3 x cubed. And here we have n into n plus 1 into 2n plus 1 upon 6. 6 is actually 2 into 3. And we have the n cubed here. The leading term is n into 2n, that is n cubed. So 2n cubed divided by 6 is actually n cubed by 3. So this also is something which takes us to calculus. And we integrate x cubed, we get x to the power of 4 by 4. But that is a 4-dimensional object. This here, which was sigma n squared integral x squared, is a 3-dimensional object, a cuboid. each of the terms here is a three-dimensional object. How do I put these together to make a four-dimensional object? Can it be done? Let us see. So now I take the first term, I take the second term, which is 2 cubed, I break it up, put one piece here, one piece here, and one piece here. And what do I get? A square. So I take the third piece, I break it up, and I get a piece here, and a piece here, and a piece here, which is also squares. And then I take the fourth term. Again, I have to break this fourth term into 4 pieces, and I put one here, one here, one here, and to fill up the space here I've got to break that up into 2 pieces, and again I get a square. So the 1 plus pink is a square. I add the yellow, 3 cubed, that's a square. I add the green, 4 pieces, which is also a square. But this is a 2-dimensional object. So how come when I integrate a 3-dimensional object, I get a 2-dimensional object? Is something wrong? Well, let's see. What is this the square of? We see the term here, 1 plus 2 plus 3 plus 4, which is, as we know, itself a triangular number. So this is actually a 2-dimensional object which has been arranged in a line rather than in 2 dimensions. So this is 1 plus 2 plus 3 plus 4, which is just sigma n, which we know is n into n plus 1. This is also n into n plus 1. So we get sigma n cubed is n into n plus 1 divided by 2, the whole squared, which is n into n plus 1 squared divided by 4. So this is, the leading term is n squared times squared, that is n fourth divided by 4, which is x fourth to the power of 4 in integral calculus. So that works fine here. And what we are seeing here really is a 4-dimensional object which we have distributed in discrete form over 2 dimensions, but it is actually the square of 2 triangular numbers. And I know now your next question is, can we add the powers of 4 to get a 5-dimensional object? That is done in Carr's book. That is done in the formula that he has here. I'm reading out from the book. It says 1 plus 2 to the power of 4 plus 3 to the power of 4 plus n to the power of 4 is equal to n into n plus 1 into 2n plus 1 into 3n squared plus 3n minus 1 divided by 30. Now the interesting thing about this is that the first three factors, n into n plus 1 into 2n plus 1, they are just the factors which occur in sigma n squared. So this is sigma n squared. As we know, sigma n squared is n into n plus 1 into 2n plus 1 divided by 6. So if I factorize 30 into 6 times 5, so this is sigma n squared into 3n squared plus 3n minus 1 divided by 5. So we have the 5, x fourth integrated gives me x5 upon 5. So we have that 5 term there. We have the n to the power of 5 because the first three terms give me n cubed, and this 3n squared gives me another n squared, so I get the power of 5. And question is, can we make it with these cubes? I hope we can, but I don't know how to do it. And this is the problem that I leave you with. Maybe one of you, like Ramanujan himself, experimented with pencil and paper. Maybe one of you will experiment with these cubes and show how we can exhibit this formula for a fifth dimension object, a five-dimensional object, using discrete objects, using cubes or something else. And if you do, please let us know here at Navnirmiti, because we can add it to this collection. I don't know how to do it, but I'm sure one of you who's experimenting with it will find the solution. I can give a hint. The hint is that this additional term 3n squared plus 3n minus 1, this is just a hexagonal number minus 2. What are hexagonal numbers? What are pentagonal numbers? This is something for you to experiment with in Experimath. But let me tell you that the hexagonal numbers can be constructed very simply. Let us do that. So what are the hexagonal numbers? The hexagonal numbers are those numbers which get formed when we play carom, and when we arrange the carom pieces at the center. The queen is at the center, and then there are 6 pieces which are arranged around it, and then again there are another 12 pieces. So it is 1 plus 6 plus 12. The hexagonal numbers are 1, 7, 19. And interestingly enough, we have this formula for the hexagonal numbers. 1 plus 6, 1 plus 6 plus 12, 1 plus 6 plus 12 plus 18. So you get 1, 7, 19, 37. And the interesting thing is that when you add these numbers, so 1 plus 7, the sum of the first two hexagonal numbers, that is 8. Then I add the first 3, 1 plus 7 plus 19, that is 27. And we've seen that this is 1 cubed, this is 2 cubed, this is 3 cubed. So why do the hexagonal numbers added in sequence, why do we get cubes? Why do the cubes, when added in sequence, give me a 4-dimensional object which is the square of the triangular numbers? There's a lot of interesting puzzles, some of which can be answered and some of which have not yet been answered. So let us Experimath in this year of Ramanujan, and I hope we discover many new examples just by adding, by joining and studying the patterns, studying how the patterns fit with each other, how they are related to each other. Enjoy yourself.